Okay, let's start the first talk of the ECR Astronomer in Australia series. Welcome, everyone. Thanks for being here. So before we begin, it's important for us to acknowledge that Aboriginal and Torres Strait Islander people are Australia's first astronomer and their long-standing system of knowledge on which we continue to build. We acknowledge the traditional custodian of the unceded lands on which we are meeting today. We are speaking today from the country of the Wurundjeri people of the Kulin Nation and the Bidjigal people. We pay our respect to their elders past and present and extend that respect to all First Peoples joining us here today. So my name is Marianne and I will be hosting this meeting with Dorota today. We are both postdoc at Swinburne University and organizing this seminar series. So if you have any question during the talk, feel free to write to us at any time. So the next speaker today is Anishya Harshan, and she's from the University of New South Wales. So Anishya, you can also share your screen now, and you'll have 20 minutes. I'll try to give you a 5-minute notice instead of 2 or 3 like I did for James.
Great, thank you. Hi everyone, my name is Anishya Harshan. I'm a PhD student at the University of New South Wales, working with Professor Kimpi Tran and Dr. Anshul Gupta. And today I'll be talking to you about how massive galaxies in a proto-cluster at redshift of 2 start to suppress their star formation and how environment affects their star formation histories. So they've known for a while that environment affects the star formation rates of a galaxy. As is shown here in the local universe from SDSS data, the star formation rates of galaxies in a cluster gradually decline as we approach the cluster center, whereas the field galaxies, which are here shown in the blue region, have more of a constant star formation rate. So this decline in star formation in cluster environment can happen due to various different mechanisms, such as which eventually either strip the galaxy off of its gas, which is the star formation fuel, and that leads to the suppression of star formation and eventual quenching, or due to its the galaxy's own internal feedback mechanisms, which stop those galaxies from forming further stars. So although this is studied well in the local universe, it's not the same case with the high redshift universe. In the cosmic noon epoch, which is between redshift 1 and 3, where the cosmic star formation rate is peaking, as we've seen here, is also the time when clusters are just starting to form and are in proto-cluster form. At this redshift, at redshift of 2, in a work done by Tran and team in the Z5 survey, which is a spectroscopic survey, they find that the star formation rates of galaxies in the cluster, which are shown here in red, have suppressed star formation compared to the field galaxies, which are shown in the blue. And in my previous work, we find that the galaxies in a protocluster at redshift of 1.6 in the low mass regime have a higher electron density compared to the field galaxies in the same redshift regime, shown here in gray. Because electron density is very similar, related to the star formation rate of the galaxy, we have some evidence to believe that probably the star environment is affecting the star formation activity of the galaxy as early redshift of 2 as well. So to dig this a little deeper, we are going to be looking at star formation histories in this work. So to do that, we are selecting the protocluster that was identified in the Z-Forge photometric survey in the Cosmos field and was later spectroscopically followed up with the Z5 survey and confirmed to be at redshift of 2.095. It is supposed to be a Virgo-like cluster, which means that from redshift of 2, as it evolves to redshift of 0, it will probably have a Virgo-like mass. We select cluster galaxies as galaxies between redshift regime of 2.08 and 2.12. And anything outside of this redshift regime, we take as field galaxies. So using the Z-Forge photometry along with other photometric bands from the literature, because cosmos is a well-studied field, and the Z5 spectroscopic redshift, we can now get the star formation histories from observations. And to do that, we are using a Prospector, which is a Python-based SED fitting code, which gives us non-parametric star formation histories. So now that we have all the tools that we require to get star formation histories, we can start looking at the star formation histories of these galaxies. We have divided the sample into 4 stellar mass bins. The y-axis here shows the star formation rate of the galaxy at a particular time, which is defined in Prospector, which we define in Prospector. And divided, the star formation rate in that time bin is divided by the stellar mass of the galaxy at the time of observation, which is here at redshift of 2. Cluster galaxies are shown in red and the field galaxies are shown in blue. And the x-axis is the time of star formation rates, and is shown in the green box depicted here. So the right-hand side is towards the Big Bang or older age bins, and to left-hand side is towards the time of observation or at redshift of 2, or more recent age bins for these galaxies. So from this, in the lowest stellar mass bin, we can see that the cluster and the field galaxies have very similar star formation histories. And there is these galaxies, so yeah, smaller galaxies have a high rising star formation history. Moving further along in the stellar mass bin, in the 9.5 to 10 log solar masses bin, again, the cluster and field galaxies have very similar star formation history. So till this stellar mass bin, environment has not been of any effect to the star formation activity in these galaxies. However, there is a difference in the shape of star formation history, which is now more of a bursty star formation history compared to the rising star formation history for the lower stellar mass bins. Moving further along, again, there is no significant difference in the star formation history between cluster and field galaxies, and these have a bursty star formation history as well. And it is only in the most massive bin that we find any significant effect of environment on the star formation histories of these galaxies. So the proto-cluster galaxies, which are shown here in red solid line, have more of a declining or a more flatter star formation history compared to the field galaxy, which is shown in the blue solid line, which has slightly more rising or burstier star formation history. Especially in the older age bin, the more massive proto-cluster galaxies are forming much more stars compared to the field galaxies. To compare it with the other stellar mass bins, we can see that it is only in the most massive stellar mass bin that the effect of environment is significant enough to change the star formation history shape. Now that we have the star formation histories from observations, we can also look at how the star formation rate versus stellar mass relation is evolving over time. So again, the y-axis here is the star formation rate at the time bin, which is described here, and divided by the stellar mass of the galaxy at the redshift of 2. And the x-axis now is not time, it is the stellar mass of the galaxy. And the time bin, so this is for the oldest stellar mass, oldest age bin, which is depicted by the green box here. And we can see that the most massive galaxies are forming much more stars, have a higher specific star formation rate compared to the low mass galaxies. And as we move further along, we see the trend start to change in the next age bin, which is 600 million years to 1 giga years in the history of these galaxies, which is shown here in this box. We can see that both low mass and high mass galaxies have very similar specific star formation rate. And as we go further along, the trends that we saw in the older stage bin is starting to reverse. And we find that now low mass galaxies are starting to form even more stars than the high mass galaxies. And as we go further along in the time bin, we see that in the most recent age bin, the highest mass galaxies have much lower specific star formation rate compared to the low mass galaxies, which means that it is only now that the lower mass galaxies are starting to build their stellar mass, whereas the high mass galaxies have already built their stellar mass in the older stage bin. So using the observational results, which show that the environment is affecting most of the massive galaxies in proto-cluster, and we are also finding that the more massive galaxies are formed much earlier. They grow their stellar mass much earlier compared to the low mass galaxies. We can now look at theoretical side of things, and so to do that we are using IllustrisTNG to see which is a cosmological simulation, and we can use the power of IllustrisTNG to select galaxies similar to our galaxies from observations, and we can trace back their histories and see their star formation and what the environmental processes that are affecting the star formation as well, if we get the similar results as we see from observations. And to do that, we are selecting galaxies in the cluster as galaxies that are associated with halos of total mass as greater than 13 log solar masses. And for field galaxies, we are selecting galaxies which are associated with halos with total mass of lower than 13 log solar masses. So once we have this selection at redshift of 2, we can now use IllustrisTNG to trace back each galaxy and their star formation histories. So we've done the same exercise as we did with observations. And now we again have the bootstrap median star formation history shown here for each sample win. And the X and Y axes are the same as before. Now the cluster galaxies are shown in brown and the field galaxies are shown in teal. We can see again that cluster and field galaxies in the lowest stellar mass bin, which is 9 to 9.5 in our selection, have a very similar star formation histories. And they have a rising star formation history, which is very similar to our result from observations and Prospector. Moving further along in the stellar mass bins range, we can see that the cluster and field galaxies still have very similar star formation histories. There is no significant effect of environment. However, the shape of the star formation histories is starting to change. It's not completely rising anymore. And as we go further along, we again see the cluster and field galaxies have quite similar specific star formation histories. However, now the peak of star formation has been pushed further back compared to the last stellar mass bin. And again, as we saw in observations, it is in the most massive stellar mass bin that we see any significant effect of environment on the star formation histories of these galaxies. And we find that the cluster galaxies in IllustrisTNG have a declining star formation history till even by the time of redshift of 2, and the teal line, which shows the field galaxies, have a rising and sort of constant star formation history, which is similar to our results from observations. Just to compare with every other stellar mass bins, we can see that the lowest mass bin have a rising star formation history, whereas in both cluster and field environments, whereas in the most massive bin, the cluster and galaxies are showing signs of suppression of star formation history as early as redshift of 2, and the field galaxies have more of a constant star formation rates. These results are very similar to our observational results, which also show the same thing, that environment is only significantly affecting the star formation histories of most massive galaxies. And most massive galaxies form their stars more early on as compared to the lowest mass galaxies, which are only starting to form their stars now. This result has been predicted in many theoretical works before, which predict that more massive galaxies form earlier, and hence they evolve earlier as well as quench earlier compared to the field low mass galaxies. And if the galaxies are within a denser environment like proto-cluster or a cluster environment, the formation, evolution, and eventual quenching will also be sped up. So now that we have our star formation histories from Illustris, which are matching with previous work, as well as our observational results, we can now use IllustrisTNG to also dig a little deeper to understand what is driving the difference in star formation histories in the most massive bin. As I said earlier, so there's this is also referred to as the nature versus nurture debate, which says that the most massive galaxies in the cluster are formed earlier, hence they will quench earlier as well. So to check that, we in IllustrisTNG, we have selected, we have taken the stellar ages of the galaxies, which is shown on the y-axis here, and the x-axis now has the stellar mass of the galaxy. And we can see that the cluster and field galaxies have very similar stellar ages. However, there is a difference between stellar ages of the most massive galaxies compared to the low mass galaxies. Most massive galaxies are about 190 million years older than the lowest mass galaxies. So did massive galaxies form earlier? Yes, they formed about 190 million years earlier, probably, than the low mass galaxies. However, to describe the difference effect of environment that we are seeing, or rather if this difference in star formation histories in the most massive stellar mass bin that we are saying is driven by the early formation or evolution of cluster galaxies. Are they formed earlier? Can that be defined first? So to answer if cluster galaxies were formed earlier than field galaxies, the answer is probably no, because the cluster and field galaxies have quite similar stellar ages, which are within the sigma error bars. So now that we have seen that there's this difference that we are seeing in star formation histories is not a effect of cluster galaxies forming and evolving earlier, we can start to look at if what environmental processes are shaping the star formation histories. Because we are seeing the most of the different effect of environment in the most massive bin, we are looking at mergers, because as James also stated earlier, the most massive galaxies are formed, they gain their stellar mass through mergers. So we are looking at the star formation, the merger histories of these galaxies. And what are plotted here is the distribution of total number of mergers, which include both minor and major mergers. That means any merger that has mass ratio greater than 0.1 of the component merging systems. Again, the teal and the or brown are shows the field and cluster galaxies. And in the first 3 stellar mass bins, as can be seen, so that is from 9 log solar masses to 10.5 log solar masses, there is no significant difference in the total number of mergers that these galaxies are experiencing. And it is only in the most massive bin that there is a slight increase in the number of mergers. So the cluster galaxies, which are shown here, have shown to have 10 total mergers by the time of redshift of 2, whereas the field galaxies have about 8, experience about 8 mergers by the time of redshift of 2. However, still there is the distribution of total number of mergers is still quite similar. So there is no significant difference in the number of mergers across environment in the most massive bin as well.
Anisha, you have 5 minutes.
Oh, great. Thank you. I'm about to be done. Yeah, so now that we don't think that the difference in star formation history that we are seeing now is probably being driven by the mergers of the merger histories of these galaxies. So we are now looking at the gas fractions of these progenitors of the galaxies that are selected at redshift of 2. And to do that, we have calculated the gas fraction of each of the progenitor of these galaxies, which will eventually evolve into being the galaxy that we have selected at redshift of 2. And that is shown on the y-axis, and on the x-axis again is the age of the universe, or the time at which the galaxies or the progenitors were existed. Again, towards the right-hand side is the older age bin, which is towards the Big Bang, and towards the left-hand side is towards the time of observation, which is redshift of 2. So we can see in the most lowest stellar mass bin, which is 9 to 9.5 log solar masses, we can see that the cluster galaxies and the field galaxies have quite similar gas fraction across time in their progenitors. And as we go further along in the stellar mass bin, we can see that the gas fraction of the cluster galaxies after about 2.5 gigayears of the universe is starting to decrease. However, it's still not very significant, I guess. And then even further in the stellar mass bin, the cluster galaxies are starting to have lower gas fractions in their progenitors early on. However, the trend is not very consistent. And it is again in the most massive bin that we find a consistently lower gas fraction of the progenitors since 1 gigayear post Big Bang and we believe that we think that it is because of this lower gas fraction from which is consistently lower since 1 gigayear that we are finding this difference in star formation history. So the suppression in star formation in the massive protocluster galaxies is probably a delayed effect of not having enough gas in these galaxies. Because by redshift of 2, they have less than 0.1 gas fraction in these progenitors as opposed to more than 0.6 in the lowest mass galaxies. So rather than this effect, the difference in star formation histories that we have seen both in IllustrisTNG and through Prospector and observations, it doesn't look like this suppression in star formation histories is directly affected by the interactions like mergers. However, it is probably an effect of where the galaxies lie and their ability to accrete more gas and to form further stars. Yep, and just to summarize, in both observations and simulations, we are finding that the massive protocluster galaxies are starting to show their signs of suppression in star formation, which is great. And we find that it is probably not a result of early formation and evolution of these cluster galaxies from IllustrisTNG, and it is an effect of a lower gas fraction in the progenitors of the massive galaxies in the cluster environment from as early as 1 gigayear of the universe. And thank you, that's about it. Thank you for your attention, and I'll take any questions now.
Thank you, Anisha, for this great talk. Are there any questions from the audience? Please raise your hand if you have a question.
I can start with a question. So you have looked at Illustris, but I was wondering if you expect the same type of results from other simulations like Fire or Eagle, or if they are very different, or I'm not a simulator, so I'm not exactly sure.
With Fire, I'm not sure because it's more of a zoom-in simulation. With Eagle, I would expect similar results because it is. They also find similar quench fractions, for example, as in the earlier universe. So I should expect that this is the case with Eagle as well.
Okay, thanks.
Anisha, what are you planning to do next? What is the next question that you are planning to answer?
Yeah, so immediately after I will look into, so now that we've seen that the galaxies have lower gas fraction as early as 1 giga, after 1 giga year, we still don't know why that is the case. Is it just because these galaxies just formed all of their stars very fast and they just have lower gas fraction, or are they not able to accrete any further gas as well from their environments? So that is one thing that can be looked into, that will be looked into. And also within IllustrisTNG, feedback from the AGN is also quite important. And the size of the galaxy plays a pretty big role in the quenching rate. So we will try to see if it is environment is better at quenching rather than the size of the AGN feedback. And on a more further scale, we can try to find observational signatures for these lower gas fractions, for example, from imaging, from HST imaging, or maybe once JWST is up and running, from JWST imaging of these high redshift galaxies.
Thank you. Do we have any other questions from the audience?
Okay, doesn't seem so. So I will then thanks the two speakers for speaking today. And also I want to thank everyone that joined in the audience. So the talks will be available online on YouTube shortly. And the next talk of this series that will be at the same time, so the American time will be after Easter, so on April 15th. So we'll send again emails to remind you about the next talks, and thank you for joining.